All right, I'm going to get started. Please have a seat, quiet down. All right, so if you guys haven't noticed yet, I think we're maybe ahead a little bit in terms of the syllabus. I think that's generally a good thing because then we can have like some review classes before the exam. So a lot of people have been asking questions about sort of carboxylic acid chapters. I don't know why they had 2 carboxylic acid chapters. They're both like pretty short. I think they're basically the same. So I guess the last class I kind of covered 2 chapters in a single day. But we're going to move on to enolates and enamines. And again, this is generally good. I think the stuff that we've covered so far shouldn't necessarily be too much of an extension over what we've seen previously. Hopefully nothing should seem entirely new that we've seen yet. Again, it's simply carbonyls acting as an electrophile. Again, if you draw them as the sort of resonance form whereby we have the carbocation deposition, then it simply becomes very analogous to, say, for example, SN1 type chemistry, and then simply performing some rearrangements. Today, we're going to discuss enolates, perhaps a little bit of enamines. And during the sort of, I think it was 2 classes ago, we began to talk a little bit about enamines and how we can generate them. I'll get to them perhaps later on, but again, the sort of general idea here is that we've primarily at this point looked at carbonyls and have seen them, carbonyls as electrophiles. Right, and there's a big parallel here, I think, between the carbonyl chapters together and then like the carbonyls and alcohols together, right? Because they have this type of versatility to them. So again, the carbonyls as electrophiles are simply thinking about these molecules in their polarized form, whereby, as I just sort of said before, we can begin to think about them as being these electrophilic species. Now as we start to get into enolates and enamines, we're going to start to think about carbonyls as a source for our nucleophile. Okay, and we're going to see this in really 2 forms. Much in the same way that if you take an alcohol, right, and you treat it under acidic conditions, it can become an electrophile. You treat it under basic conditions, it can be a nucleophile. You begin to see similar things, I think, with carbonyls. What I'm saying is nucleophile. Certainly, we can think about this carbonyl as also being a nucleophile, but we didn't really discuss too much about this. But again, as we'll see, if you take a carbonyl and you treat it with a base, we'll discuss what types of bases can do this. What we're going to get to is these 2 sort of resonance forms, right? So these are sort of enolates. You can imagine the enolate as having a negative charge on the oxygen, or you can imagine it having a negative charge on the carbon and simply resonating between these 2. Right, back and forth. Now, if I were to ask you guys right off the bat, which of these 2 do you think is more stable? Which one would you say? First one, why? Yeah, right, exactly. So generally, this is how we'll draw enolates. Right, so generally when we're going to look at enolates, we'll generally draw them. This is kind of analogous. There's another analogy here between, I think, enolate chemistry and perhaps the carbonyl chemistry up here. So we draw them this way, we can sort of think about them reacting as this way. In terms of enolates, there is certainly chemistry that involves the oxygen being the sort of nucleophilic component to this. Which is sort of, there's differences here. We can discuss O-alkylation versus C-alkylation. Primarily for the sake of this course, we're going to really refer to in terms of enolates as reacting from the carbon. Okay? So certainly there are plenty of examples in the literature where you can coax an enolate to actually have the oxygen attack. Okay? But to sort of keep things less confusing, we're going to really refer to the sort of nucleophilic behavior is what we talk about as C-alkylation. So we'll be looking at the negative charge on this carbon, and it's really that carbon-based nucleophile that we're going to use to begin to do chemistry. In many ways, this is going to be analogous. You know, we've discussed how this is organic chemistry. Organic chemistry is this study of carbon-containing molecules. Carbon-carbon bond-forming reactions, thus, are an integral part of this. And so anytime that we can have a carbon-based nucleophile, right, we can begin to add to that sort of carbon sort of scaffold, that's going to be a valuable reaction. And for these reasons, enolates, and specifically enolate chemistry where we refer to C-alkylation can be very, very valuable. All right, so let's discuss the sort of pKa's a little bit. So we'll be referring to really two different types of enolates. There's our sort of standard enolate that would come from something like acetone, basically what I showed there. I apologize for the redundancy here. But this is sort of the primary enolate that we're going to see. This relative, obviously every reaction is reversible. The pKa of this reaction, all right, if we think about our standard, say, methane, right? Again, that's not acidic at all, right? Methane pKa is somewhere about 50. Once you're able to stabilize the enolate up in this sort of up into the oxygen, it actually helps make these a lot more acidic. The pKa, again, depending upon what you have, it's somewhere in the 20s. We'll just say 20. I've seen 25. So it's going to depend somewhere in that range. But basically, what this means is that you have to have a fairly strong base to actually deprotonate this, right? And the bases that we will generally see that will do this will be things that have pKa's that are higher, okay? And as you guys have sort of learned, right, the pKa of something like a sodium hydroxide is only somewhere around like 15, right? And really any alcohol that we've discussed, the alkoxide is generally in the teens. So what you would likely need, right, is the next step up, not an oxygen-based base, but a nitrogen-based base. So primarily what we're talking about when we talk about generating enolates is nitrogen-based bases. In particular, the one that's used most widely is lithium diisopropyl amide. So it'll be abbreviated as LDA. So it's basically lithium diisopropyl amide. Okay? And so this will be the primary base that we use to make the enolate. And so if you want to make your enolate, you've got the ketone, you simply treat it with LDA. Yes?
Why does it have a higher pKa than normal alkoxide?
Why does it have the normal? That's actually a really good question. So the question is basically asked, if you've got an alkoxide, it's around 15, right? And the question that was asked is referring to this as like, well, that is an alkoxide, so why isn't it? Anybody might want to take a gander? This is something that I've often thought about as well. Can you think of anything?
I thought maybe less, like a double bond carbon.
I think that's actually a great thought, right? You have this enolate, you have this oxygen which has a negative charge, and not only is it an oxygen that has a negative charge, right, but it's an oxygen that's resonance stabilized, right? So it's a fantastic question. I don't have a great answer for you. I've often thought about this myself. What's one of the things that's happening, though, once you move that negative charge up in that oxygen, though?
What's that?
When you go ahead and you try to put that negative charge in the oxygen, what functional group that we've often referred to as a thermodynamic sink do we effectively lose? Right. And so I don't know what the exact answer is, but you could rationalize it at least in terms of thinking about the relative stabilization of the carbonyl. So you're right to an extent, right? Hey, looks like it would be more stable, but the most prevalent resonance form would be the one with the oxygen on the negative charge, and perhaps that is disfavored in part because of the fact that you are losing that ability for it to be a carbonyl. But it's a great question. I don't have a much better explanation for you than that. But that's been something I think I might have asked the exact same question when I was an undergrad. But at least you could rationalize it in terms of the carbonyl. Okay? All right, so there is that. But again, you need a very strong base to generate it. The other class of enolates that we'll sometimes talk about will sometimes be 1,3 diketones, 1,3 ketoesters, 1,3 diesters, basically molecules where you have a carbonyl separated in this sort of form here. Okay? All right, and so in cases like this, right, now this molecule is actually much more acidic, and what I'm talking about here is these protons down here. Okay? What I'm primarily talking about is that sort of enolate, right? So deprotonation of this proton, resonate that negative charge up into the other oxygen. As you can see, this is actually perhaps a much more stabilized enolate than the one above. The pKa of this now is actually lower than an alcohol. So the pKa here is actually about 11. Why might this be more acidic? Right, so it's doubly, it's got carbonyls on both sides, right? From the standpoint of this guy here, now you can imagine the resonance form or the negative charge. In many ways, it's almost like, right? It's almost in many ways like an extended carboxylate, right? So the same question could often arise here. Why? This looks to me like a extended carboxylate, so why isn't the pK of that lower than, say, for example, a carboxylic acid? Great question. But again, it could have something to do with a similar type of system that carbonyl is now basically no longer carbonyl, whereas in the case of carboxylic acid, the resonance forms are both oxygens. Lots of questions in organic chemistry, obviously. All right, so as you can imagine, if the pK of this is about 11, now we don't need such a strong base. This is perhaps one of the advantages, and we'll discuss these a little bit later on. Now we can get away with, say, for example, alkoxide-based bases. Say, for example, potassium t-butoxide. Right, that's potassium t-butoxide. Right, the pK of t-butanol is somewhere in the 17 to 18 range. A lot of times we like these bulky bases if we want to generate enolates, right? So we thought about what are good bases, things that are bulky that can't necessarily do nucleophilic activity. So you'll notice both of these are very bulky bases because we simply want them to deprotonate, right, one of the protons and get us to that nucleophilic component. So again, here's the kind of two different kind of classes of enolates that we'll refer to. In the case of a 1,3 diketone or 1,3 ketoester or 1,3 diester, it should be fairly clear which enolate's going to form, right? It's going to be that one in the middle. You can imagine that in cases like acetone above, obviously acetone's symmetric, so it doesn't really matter which side we deprotonate. But if we can begin to start imagining non-symmetric diketones, that would have an effect, right? Okay, so again, in this case, it's symmetric, so we treat it with the base. Doesn't matter which side the enolate forms on. But if we have a situation where we have, say, for example, an ethyl on one side, an ethyl on one side, a methyl on the other. Right, now we're going to have maybe E or Z on that side. That's another level with enolate chemistry. There's actually a lot involved. There's many layers. Enolate chemistry is probably teach a course just on enolate chemistry alone. But for the intents purposes of our class, we won't really worry about the EZ enolates. If I give you an E or Z enolate, I think I had a question that had one on the final, but I sort of gave it to you. So we won't discuss the relative ways in which you can make those different enolates. But clearly here you see two different regiochemistries. Yeah, so we see two different possibilities here. We can have the enolate on this side, or we can have the enolate on that side. As it turns out, there are ways in which we can make one enolate over the other, and so we'll sort of have this little trick if we want to make a specific type of enolate. Okay, if I had to ask you from those two enolates, which one you think is more stable, which one might you assume? The one on the right. Why? Right, the more substituted alkene, right? If I were to ask you which one is the kinetic, which one's going to be protonated faster, which one might you say? If I'm talking about the actual deprotonation, right, HA or HB. HA, why would HA be kinetically more accessible? So from a steric standpoint, right, HA, more sterically accessible, right? So in this way, right, you'll do that kinetically. And again, there are parallels here in many ways. Perhaps if you think back to Organic Chemistry 1, there are some parallels here, right? When we discussed elimination, right, we had sort of Zaitsev's rule, right? The more substituted alkene would form when we had a sort of non-sterically congested base, right? If we had something that didn't really worry about the sterics, perhaps you would get to the more substituted one, right? That would be Zaitsev. If you had the bulkier one, it would go towards the less substituted. So that's not the parallel that we're going to draw here. We're going to use these bases, but there's going to be another little trick that we can do. So this is the kinetic forms fastest. Okay, what do we call the one that's more stable? This kinetic product or intermediate. This would be the thermodynamic intermediate. And I ran out. So this is going to be the thermodynamic intermediate. This is going to be the thermodynamic enolate. This is going to be the kinetic enolate. Okay. So what does this mean in terms of the chemistry taking place? Well, what it means is that if you will have a system set up, right, where your reaction is irreversible, you're going to get this one, right? If you have a system where it is reversible, then you're going to get this one, right? So again, if it's reversible and you let it go long enough, right, you're going to get to this point. So how do we take and make enolates and have conditions that might allow it to be irreversible or conditions that might allow it to be reversible? And so it turns out that this just has to do with stoichiometry. Yeah, you were going to say something? Say that again? So there's no water necessarily generated here, so it's not really that case. But one of the things that you can do is, again, we have a pretty strong base. So as it turns out, if you have an excess of base, maybe low temperatures, well, short reaction times, right, we'll be able to primarily get the kinetic product, and I'll explain this over on the other half of the board in a moment. If we have excess ketone, right, maybe higher temperatures, maybe room temp or higher, right, you allow that equilibration to take place to get thermodynamic. Maybe longer reaction times, like these are all things that could, maybe not the overall reaction, but at least in terms of the time that you allow the base to start with the ketone, right, then you're going to perhaps get the more stable enolate. Now, the book primarily, I think, talks about these two factors, right, excess base or excess ketone. In the case of excess base, right, what's happening here in the case of excess, actually maybe we'll explain it first in terms of excess ketone and then we'll resort back. That's probably the better way to sort of think about it. All right, so if we have, say, 1.1 equivalents of ketone, right? And we treat this to a base. First thing that's going to happen right away, right, is that we're going to get this enolate, okay? Now what happens, right, is that if you have more ketone in here, some of this ketone can serve as a base to deprotonate this ketone. And it can go in one of two ways. It can either deprotonate, say, HA and HB again. It can either deprotonate HA, in which case it's just going to be redundant, right? You're just going to regenerate the same enolate. And maybe that would happen right away. But over time, what's going to happen is you're going to allow it to react with HB. Okay? In which case you would generate that ketone there, right? And so the fact that you have this slight excess basically gives you the ability, right, to over time, right, it's going to reach the thermodynamic. You basically give it this reversible nature. And certainly it can deprotonate the HA, right? But again, that whole process, you're basically just regenerating the same compound, right? But over time, what's going to happen is you're going to get to the more stable of the two, and you're going to get to the thermodynamic product. Right? Does that make sense? Okay. Now, if you've got a lot of base, right, if it has more ketone in it. If you don't have any of that ketone in it, right, then what becomes your proton source that would otherwise make this reversible? There's only one real thing in there, right, because you've got all enolate, right? If you've got an excess of base, then all you got is this enolate, and you got your proton source is what? The conjugate acid. Right? And again, the pKa differences of those are pretty big. Again, over time, perhaps if we let it go really long at room temperature, perhaps the conjugate acid would allow to protonate and go back the other way, which is perhaps one of the reasons why we sort of keep it in this. But again, that's going to be a much less acidic proton, right, than, say, for example, the alpha proton to the carbonyl, right? So again, this is how you would perhaps get that chemoselectivity, right, of the less substituted versus the more substituted. Does that make sense? Maybe? All right. All right, so this is how we generate the enolates. So we've learned a couple different types of enolates. And the next question really becomes, so why do we care? And again, I sort of alluded to this earlier, but the idea is that once you have an enolate, it's a nucleophile, right? And that's just it, right? It's another type of nucleophile. So virtually any electrophile that we've seen could in principle react with this nucleophile. So again, how much of chemistry is simply a nucleophile reacting with an electrophile? That's like everything that chemistry is, yeah. I'm saying that the proton of HA is more accessible sterically. right? And so think back to elimination chemistry, right? The bases that I showed you guys were big, bulky bases. So there's going to be a kinetic preference for them to go after the more sterically accessible proton, which is HA. Does that make sense? But over time, right, you can, especially if you have excess ketone, you can imagine that this process would be reversible, like everything that we see, and thus it would go to the thermodynamic product. Make sense? Yeah.
Why is it a reversible reaction to the same thing?
It is the exact same thing. No, but it's still a reaction, right? It's like a reaction that leads to the same product.
So
Yeah.
what's it interacting with it? That's
So it's like another molecule, right? Again, we have a slight excess, right? And that's the difference, right? That's the difference right there. If there is none of this, right? If we have an excess of base, then in principle there would be none of this. So the only way that it would get reprotonated would be to react with the conjugate acid, which is going to be a much slower process. Yeah. I don't know. They're going to be probably fairly close, but I'm sure that they would have different pK values. I hadn't really thought of this, but I would assume that, let me think about this. I'm sure they do. I'm trying to think of which one would be higher. I can't really think off the top of my head, but it's irrelevant. Oh, excuse me. Maybe. I don't know. Maybe. No, it's a good question, but I just showed you another way. So there may be bases. We have to look them up. Draw the analogy to T-butoxide, for example, is more basic than counter T-butanol is less acidic than, say, ethanol, but that's technically another carbon removed. I don't know. Maybe. Yeah. Mm-hmm. 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 So that's always the big difference. I mean, you've got two things going on there, because there is the difference in pKa value between that internal proton is so much dramatically different, right? It's like 10 times. Remember, the pKa is logarithmic, right? So that's basically telling you it's like 10 to the 10th times more acidic to deprotonate that middle one. In addition, so kinetically, it'd still be more acidic. And the other thing about those is that, and I didn't bring this up, but it could sort of perhaps answer your question as well, is that I sort of drew the molecule like this. This actually isn't how they, this isn't actually how they generally exist, even. So in fact, when you look at a molecule like this, the actual more favored tautomer is the other tautomer. So that tautomeric form is actually how they would exist. In which case, now this is even more accessible, right? So it's sort of irrelevant. Okay. But good question. You made me forget what we're talking about. We can react with any electrophile we want. Any more questions before I? Okay. All right. So again, what we have now is a new nucleophile. We can imagine this reacting with virtually any electrophile that we want, right? And so, and again, I often like to draw it as this enolate. If you want to draw it as the negative charge on this group, that's fine as well. But this is generally how you'll see it draw, so it might be worth it to just get comfortable with that. But again, if you treat it with any electrophile, what's going to happen is we're going to get alkylation at that carbon. And so, what are some of the electrophiles that we have, right? Well, you can imagine, one of the very first types of electrophiles that we learned about were alkyl halides, right? And so as you might imagine, if you generate an enolate and you treat it with, say, for example, an alkyl bromide, right, you would actually perhaps undergo C alkylation. Turns out there's ways to do this and get O alkylation, but kind of besides the point, we're going to focus on C alkylation. But the other thing, and this is what a lot of the chemistry that we're going to talk about within enolate chemistry, is really the reactions of enolates with other carbonyls, okay? So if you could imagine, say, for example, an enolate reacting with, say, for example, an aldehyde, right? So we have this R2, R1. So what's going to happen in this chemistry is we're sort of combining what I just taught you with what we've been talking about previously, is that the oxygen and carbonyl, is going to behave as an electrophile, and the reaction that you're going to generate after protonation is going to be this compound here, okay? And so this is one of the first reactions we're going to learn about enolate chemistry. Again, this is simply referring to one. When I'm saying this, what I mean is water, perhaps, because we'll discuss sometimes under acidic conditions, something else can happen. But this first reaction is simply called an aldol reaction. Okay, so if you have an enolate and you react it with, say, for example, an aldehyde, you can do that with a ketone as well. It doesn't work as well, and you might imagine there's some selectivity issues in them. So generally, the aldol reaction that we see a lot is with aldehydes. And then we'll just quickly show you another reaction. If you take this molecule, and you can even do this during the workup, so it doesn't necessarily mean it needs to be 2 steps. But if you simply work this reaction up under acidic conditions, we discussed this, sometimes you can actually run aldol reactions even under acidic conditions. We can actually eliminate water as well. Okay, so you can, under acidic conditions, you can actually drive out water. It turns out this process isn't one like we saw previously necessarily, right, where we need to actually drive water out of this reaction. Certainly that could help, right, if we added molecular sieves, perhaps this might make the reaction faster. But this product that we form is and will form fairly quickly. Sometimes doing an aldol reaction can be difficult, in part because of the subsequent elimination reaction. So what's happening here mechanistically is simply an elimination, right? Again, there's many ways that we could perhaps draw this reaction, but I think it's best just to think about it as being protonation. Right, we're going to have that compound there, right? And then again, the conjugate base, whatever that may be, simply going to eliminate water to get to that molecule there, okay? So in this case, what we're generating is what's referred to as an alpha-beta unsaturated carbonyl. So usually you say like alpha-beta unsaturated ketone, alpha-beta unsaturated ester, for example. And as I just sort of pointed out, these molecules are actually a thermodynamic sink as well. You don't necessarily need to drive out water for this reaction. Why might that be the case? What looks like it might be more stable here than here? This is sort of an important concept that's going to come up. Is that? Yeah, resonance, conjugation, the sort of same thing, right? Is that what you have here is an extended pi system. Okay, this is something that we'll see time and time again. Oftentimes, and this will come up specifically when we refer to Diels-Alder chemistry in a few weeks. This, again, if you sort of think about the resonance form here, you can imagine several additional resonance forms. But again, the way that I like to think about conjugation as being a stabilizing force is that you effectively take the electrons in that pi cloud and you allow them to dissociate between twice as many atoms, right? So instead of 2 electrons in that pi cloud being in between 2 atoms, now you've got 4, but they can sort of spread out among 4 atoms. And again, if you sort of think of the claustrophobic nature oftentimes of electrons, that's at least one way that you can think about it. It's one of the ways that I often think about it. And again, as we'll discuss later on in the chapter, we don't even think about these as being separate pi orbitals. We think about them as being one long conjugated system. And so there's a lot of chemistry that's associated with sort of extended pi systems. So actually, this is a good transition into the next reaction we're going to learn. So this is called an aldol reaction. You want to take a guess at what this one's called? What kind of chemistry is this when you lose water? We've seen this in the past. Condensation, right? So we've seen condensation chemistry in the past. Say, for example, any time that we're losing or generating water in the reaction, right? In this case, what's happening is the reaction, we're sort of generating water. So as we've talked about, say, for example, acetal formation or imine formation, I sort of have referred to all these reactions as condensation reactions. And in that same way, this is an aldol condensation. So when we refer to an aldol reaction, what we're referring to is simply the reaction to the sort of beta hydroxyl ketone. When we refer to aldol condensation, what we're talking about is this overall process to the alpha beta unsaturated ketone or ester, alpha beta unsaturated carbonyl. Yeah.
Isn't it microbial on protein over the alcohol group?
So the question is acidity of that carbonyl. Certainly, in fact, what may happen is this might be protonated first, and then this is protonated. So what you're referring to is the relative acidity of intermediates. And so if you start thinking about which one would be protonated first versus which one would be protonated, which would lead to a productive reaction pathway, that's the big difference. So certainly, this might get protonated before this gets protonated, but what's that going to do? Nothing, exactly, right? So it's important to recognize that every reaction is reversible, and so while it's good thinking about those things, it's important to recognize that that's all reversible. And perhaps that could even help assist in this process, right? It could protonate here first, and then perhaps the second protonation is actually intramolecular. Or perhaps even assist, right? You could imagine the same. Or you could also imagine a system like this where it all happens. Whoa, I don't like that actually. Yeah, never mind. No. I was going to draw something, but actually it doesn't work that way. All right, so a good transition here to another electrophile. Again, we've talked about it briefly before, but we talked about alpha beta unsaturated carbonyl compounds, right? And as was just brought up, right, these can be, electrophilic at sort of 2 carbons, right? So we discussed this when we went off on that tangent about cuprates, right? And we talked about how cuprates can attack here, right? And how Grignards and so forth will actually attack here. In the case of So again, the resonance form that would dictate this one would be the oxygen on this, the electrons on this oxygen with the full lone carbocation here. The resonance form that would show that one would be if you push the electrons a little bit further. Right. We have the carbocation there. Okay. And so again, the chemistry of, so we discussed this a little bit previously. Don't want to get too much involved in this because this gets into heavy physical organic chemistry. But we discussed a little bit about how cuprates were a little bit softer, right? A little bit softer nucleophiles, not as charged as the, say, Grignards or alpha lithiums, right? And so where the LUMO resides really was what drives the reaction. Sort of alluded to the fact that the LUMO of this system is actually here. Again, there's just a molecular orbital explanation behind it that I want to get too far involved in. But the important point is that when you have a sort of an uncharged, something that's not super charged, or something where the electron density isn't so concentrated, it is in something like a Grignard, the chemistry will often go towards this carbon. Do you have a question? Or you just checking? Okay, no, it's okay. So in the case of an enolate, enolates are a little bit softer, right, in terms of nucleophiles, right? That charge is a little bit spread out, and so much in the same way that a cuprate will add to the beta carbon, enolates will also react to that beta carbon. Okay, so if you have an enolate, now we're going to have R1, I'll stick with the previous scheme and I'll give that an R3. But if you have an enolate like this and you treat it to an alpha beta unsaturated, R2, R1, this will stay consistent. If you take this enolate and you treat it with an enone of some type, an enone or an enolate, we're going to have it attack at that beta carbon again. There's a lot of arrows perhaps moving around the system, but all I'm doing is I'm attacking from that resonance form, right? So the arrows in here are the same as the arrows here. Attack is going to come from that carbon. Okay? And when this attacks, the product that you're going to end up getting, right, is O alkylation, R2, it's going to be a molecule enolate something like this, right? And so if I can just color coordinate so you guys can see what's happening, because I know now we're getting to a fairly long chain. Put those blue electrons there, right, are attacking and making a bond between this carbon and this carbon here, right? And then what's happening is purple electrons here, right, are just moving over one, so they're going over to here, right? Now we've got a subsequent enolate, okay? There's actually a class of polymers that you could imagine would be based upon this continuously reacting with more equivalents of acrylates. These are called polyacrylates. But your standard reaction, you can sort of control stoichiometry and you can actually get it to stop at this point such that when you work the reaction up, what you now have that molecule there. Okay, so now you've got basically added 1,4. Obviously, the enolate is going to get propanate. It's going to go to the enol. The enol is going to tautomerize back to the keto form. So you'll get molecules like this. Again, you know, draw the mechanism of this on your own. Make sure that you know this. Perhaps I think one of the challenges with once we start getting these longer branched carbon chains is that sometimes we lose track of where everything is. So it's important that you slow down and make sure that all the carbons that you have, conservation of mass, conservation of charge, and sort of make sure that it makes sense, okay? And so this reaction also has a name. This is called a Michael reaction. Now somebody sent me an email that was asking about name reactions. and whether it's worth it to know all the different names of the different reactions. It's not, I'm not going to test you on it. I'm not going to like be like, show me what a Michael reaction is. But, because, you know, the name of the reaction is just kind of a way to describe it. But as synthetic organic chemists, this becomes part of our language, the name reactions, because as you guys have seen, you guys have already learned a lot of different reactions. And so a lot of times, some of the most valuable reactions have had names associated with them just because there's no other way, you know, there's no quicker way to describe them, okay? So if you are an aspiring synthetic organic chemist, it's probably worth it to know the names. If you're just trying to get through the course, if the names can help you remember them, that's fine, but I'm not going to test you on them. Yes?
So, microreaction formula is alpha beta unsaturated.
Exactly. That's all that we just saw, right? We've just done 4 reactions in enolate with an alkyl halide, just that nucleophile with that one, right? With an aldehyde, with an aldol. Aldol condensation is simply an extension of the aldol where you're condensing and moving water. And the Michael is simply the enolate attacking an alpha beta unsaturated. Yeah. So workups, after every reaction you do, the workup is formally the final step. Say, for example, when you ran a Grignard reaction, right, you have an alkoxide at the end, and generally we don't want to work with things like charged molecules at the end. It's more difficult to do. Oftentimes we wash away salts and so forth in the aqueous, right? You guys have done aqueous extractions, and so you generally want to take your charged species, right? But again, even if you took this and added it to water, it's going to protonate. So the workup is simply the subsequent step after the reaction. Every reaction generally has some type of workup associated with it. Not always, but oftentimes you run a reaction under acidic conditions, you neutralize those acidic conditions. You run it under basic conditions, you neutralize those basic conditions. So it's just the subsequent process. In this case, the workup would simply be take this, dump water in it. Okay? All right. All right, so those are 2 times. Let's discuss another one. Okay, so we've seen enolates react with aldehydes. We've seen enolates react with alpha beta unsaturated compounds. The last reaction we're going to discuss is, well, it's not the last reaction we're going to discuss, but the sort of next logical progression, I think, is the reaction of, within the sort of this carbonyl range, is reactions of enolates with esters, okay? So, if you have an enolate of some type, okay, and you treat it with, say for example, an ester of some type, again, you can go through the mechanism of this and do the same thing that we did before. So there's parallels drawn here between, say for example, a Grignard reacting with an ester and this enolate reacting with the ester. So the first thing is going to be the same, right? We're going to attack this ester. Okay. Once we attack this ester, what's the next thing that's going to happen? Right? Same thing that happened with, say, for example, a Grignard reaction, right? Or a reduction of an ester with LAH, right? We're going to eliminate the ethoxide. Okay. Now, in this case, if we were doing an LAH reduction or we were doing a Grignard, what would be the next thing that would happen at this step? We would add in again, right? If this was a Grignard or this was LAH, right? We've seen in cases in the past, right? The esters are in fact less electrophilic, right? Than a ketone, right? The ketone would generally be more reactive than the ester. So oftentimes what would happen, say for example, You know, you guys saw this when you added, you know, ethyl benzoate and you added phenyl Grignard to it in that Grignard lab, right? It added in twice because you made the ketone and then the ketone got added in again. But it turns out that in the case of this reaction, you take an enolate and you treat it with an ester, it doesn't add in again. Why might that be the case? There's a couple of reasons. Why it stops here, you don't add in again. What might happen that would prevent it from adding in again? It's along the right line. Yeah, I mean, I think we're good there. We can take it a step further, right? So the recognition is that this is what we saw previously, right? A 1,3-diketone. And so we can rationalize this in a couple different ways. The one way would be that there's a tautomeric form. Okay, so that's the one, perhaps, argument, right, that there's this tautomerization, right? And now it's not actually a ketone, right? You've got, well, this is now an alkene, but even this guy over here, this is kind of an extended carboxylic acid. But another thing might actually happen, right? If you were going to react a nucleophile with this compound, every nucleophile is also a what? A base, right? And so given how acidic these are, what would probably happen on this molecule even before it reacted with, it would probably be propane, right? And then it's definitely not going to be electrophilic. So this is one of the last, at least, classes of enolate reacting with an electrophile reaction we're going to see. This reaction is called a Claisen condensation. There's another reaction actually called the Dieckmann condensation. Okay, the Dieckmann is actually the intramolecular process. So the Dieckmann, it's the same thing, but you'll see these two different names. Okay, again, we're not losing water this time, but we're losing the ethoxide, so it's sort of similar in that extent. It's not formally water generating, but it's an alcohol that's being formed. This is the inter, so this is like a drawn. This is intra. I don't know why they needed two different names for the same reaction, inter versus intra, but you'll see these two different names, and it's the same thing. So, okay. Now the Dieckmann, again, it would be you're forming cyclic beta ketoester. Your beta ketoester. This just happens, right? This is unstable. This is kind of what's been brought up time and time again. Carbonyls are really stable. So a hydrate, a hemiacetal, hemiacetal. One of the few examples where we'll see something not be a carbonyl is in cases like this one here, right? Why? And this is a unique case. Why? Because of the conjugation. Exactly. Yeah. Did you have your hand for a question, or you were going to answer? Yeah. Okay. All right, so let's do a mechanism. I'm going to do a mechanism of a reaction that's called a Robinson annulation. It's formally a combination of a few of the reactions we've seen, but I'm going to draw the reaction. I'm going to give you guys a little bit of time to actually think through it, and then we'll sort of discuss it. And I'll just show a famous version of the Robinson annulation to make a molecule that's been widely used. I actually have run this reaction. It was one of the first reactions I ran as a graduate student. And the reaction is going to be Okay, so what's going to happen is we're going to take these two molecules together. The first step will be a base. Okay, so we'll start this with a mild base. And formally, just to sort of, again, you can actually do this process, subsequent step, under acidic conditions. I'm now sort of questioning, we'll go for it and then I'll explain it later on. So we'll try to keep this analogous. This isn't actually how the process is run, but we'll discuss. So what we'll do next, we'll basically treat this as a three-step reaction process. We'll say LDA, followed by acidic workup, okay? And the product that we're going to generate is going to be this product here. Okay. And I'll just color coordinate there for you guys, just to hopefully make it a little easier. Okay. So this is a Robinson annulation. It's going to involve a couple different reactions. Okay. So go ahead and start it off. I'll get you guys going. What do you think the first reaction is going to be? We're going to treat this with sodium bicarb. Maybe I should have just showed you guys previously. Let's say T-butoxide. Stay consistent. Okay. What's going to happen when you take that molecule and treat it with potassium T-butoxide? Yeah. Okay, so we're going to deprotonate that first, and then go. I want to see pen to paper. Trying to figure this out. What will I figure out what I'm going to talk to you guys about once we go through this? So we'll be treating this with the methyl vinyl ketone. So what's going to happen when I treat this molecule with methyl vinyl ketone? This and this is going to happen. Yeah.
What is the negative charge onto the oxygen?
Sure. There's a resonance form. Same thing. I was just.
How do you even know which one's going to react?
Well, I told you guys that the oxygen can react, but for the sake of this course, we're never going to see that. It gets a little bit more physical, organic, hard, soft. It's kind of like the similar arguments to the cuprate Grignard argument that we were making with phenols. But for the sake of this course, we're just going to focus on C alkylations of enolates. Okay? So you're right. I mean, these are simply resonance forms. So there is no difference between this molecule and this molecule. So if you're asking why is he drawing this rather than this, it's the exact same molecule. There's nothing wrong or right about either one of them. Organic chemists tend to like to draw them like this, simply because that's how it more likely exists. The other resonance form simply is a better resonance form to help think about the chemistry. Yeah. Okay, so what's going to be the next step? Yeah.
The double bond amplifier and attract the electrophile.
So this is now our electrophile. Okay, and the question becomes, let me just redraw it. With more space. So then there's our electrophile. So where do you want to attack?
The carbon double bond is
Here?
no.
Here? Here?
Oh.
Here?
Yeah.
Here?
No.
Here.
Yeah. I think.
Okay, he thinks.
I think. Sure.
Be sure. All right, well, let's go there. See what we get. Okay. Anybody else? Are you kind of stuck here, though? All right, so you're running through a mechanism, right? And you do something, there's nothing wrong with that. Well, maybe there's something a little bit wrong with it. But, formally, I think for where you guys are, there's nothing wrong with that as a step in your mechanism, right? But the problem is it's not helping you moving forward. Yeah. Right, so if we instead tap the beta position, right, because the issue here, let me just sort of tell you guys really quickly, one of the issues here is that now you have this sort of carbon-carbon bonded, basically two carbons. We don't see anything like that in this molecule, right? We don't have any of those carbons that are like that. Where instead if we attack at the beta carbon, which is a Michael, right? Now we've got this sort of more branched system here. Okay. So again, if it helps to sort of color coordinate. Okay. Is it going to exist as this enolate, or what's going to happen once you generate the enolate? I'll just tell you guys that after this step, what we're going to do is we're going to work it up. Okay, so at this point, we'll work it up, and we'll take it on to the next step. Okay, we take this molecule, we treat it with water. Somebody was asking about the workup step, right? You're going to protonate the enolate, then you're going to tautomerize, and you're going to end up with the ketone, right? Okay. All right, so now we have this molecule, and what we're going to do is we're going to treat it to LDA, okay? And perhaps this is a step in the synthesis that many people might say, well, it's going to do this first. And yeah, you're probably right. But it's not a productive step. All right, so what's your sort of first intuition? You take this molecule and treat it to LDA. What might happen first? What's the most acidic proton in this system here? Yeah. Yeah, it's probably this one here, right? But it's not going to help us too much. So again, the reaction is going to be reversible. And so it's at this type of step that we have to give ourselves a little bit of wiggle room to an extent and ask ourselves what's the product and ask ourselves, is there any hints that perhaps the product provides us that might suggest the type of chemistry that we want to do and where the sort of molecule might want to become a base? Yeah. So you see an alpha-beta unsaturated ketone. Right. Everybody see that? So see where that aldol condensation is? So you look at this molecule. I have my guy here with the carbonyl here. I've got my sort of molecule here, right? And really what I want to do is I want to make a bond between this carbon and the carbon in a way in which case the final product, right, is an alpha-beta unsaturated ketone. Right? And the way that we can do that is by making the enolate at this carbon and having it react with one of these carbonyl. It doesn't matter which one, the molecule's symmetric, right? Now, once we react with that, right, so the base is going to simply deprotonate. Add here. Again, I'll color coordinate in blue so we can see that guy in there. Right? And then what's going to happen, we'll protonate, yeah?
Wait, you just add that nitrogen, that carbon.
Yeah, so sorry, workup followed by, yeah, I'm just saving board space. We're running out of time. I want to show you guys one more little thing. So this would be following LDA. Turns out you can actually do this process in a single step, so you don't necessarily need to work it out. But again, I'm just sort of showing that process, right? And then when we get to here, just look back at your notebook for what's going to happen, right? We're simply going to do what I showed you guys earlier in terms of an aldol condensation. We're going to protonate. And under that acidic workup, we're going to eliminate water to facilitate the final condensation process. Okay? So this overall process is called a Robinson annulation. It's a really valuable reaction. Okay, so, God, this is flying through material here. That's kind of it for enolates in a way. I want to, in the remaining time here, I want to sort of transition from enolates. So again, all that this is, you generate these enolates. Again, it's a way to generate a nucleophile, and then you can simply treat it to these different electrophilic sources. Know all of these mechanisms. Know that you can sort of make one enolate over the other, and you should be able to see that this is going to be a versatile process. But these reactions shouldn't seem, once you sort of understand the generation of the enolate, they should look a lot like other reactions that we've seen. Yeah.
Could you show us how the second to last thing got to the quantum dot, the double bond?
How this?
Yeah. Thank you.
Following the workup, under slightly acidic workup, what's going to happen is you're simply going to do...
You need two chromations or nitrogen?
Well, no, the workup, this isn't going to... You don't need like two equivalents of acid per se. Just the aqueous workup itself, or... Yeah, a lot of times you'll treat this with like dilute acetic acid in water. This overall process, like when I ran this reaction, no, you can actually run the overall condensation process, I believe, under acidic conditions. Maybe I'll mention in a second. But yeah, so once you generate this guy again, it's just this isn't anything new. This is simply just two reactions that you've seen tied together. It's just Michael addition followed by aldol condensation. So that's all that this is Michael, right? It's a Michael addition. And then this is simply an aldol condensation, which is what was brought up earlier. You see that eno and you recognize that as something that we've seen in the past, and then you can do that. So I think it's a good opportunity. Again, we've got maybe about 6 or 7 minutes left. I'll sort of introduce you guys. Yes?
Good question. We were talking about including the pasta, and then is it kind of like a pseudo
Yes, that's exactly what it is. Yeah. All right, so this reaction is actually a really very famous reaction in synthetic chemistry, and this is a good opportunity to sort of transition to the next reaction. Okay, and part of the reason is that when you have molecules that look like this, what you might notice, right, is that we have a stereocenter in this molecule, right? And that stereocenter, if you think about it, the products that we formed when we had, say for example, this enolate here, the product that we generate, right, and the stereochemistry that we get is basically going to come down to what? Which carbonyl we attack, right? So absent from anything that's going to make the enolate want to go after one carbonyl over the other, it's going to have an equal chance of going after this one and is it going after this one. What if, say for example, you could run a reaction like this and you could coax the nucleophile here to go after only that one. What's that? How would you protect the other one over this one? Yeah, it's not that simple. Yeah, you can't, right? Because it's impossible to take a molecule where you have two functional groups that are otherwise equal and get them to react. The only thing that really discriminates between these two carbonyls is that they are what we call prochiral, right? If we change one of them, right, this molecule is not chiral, right? But this stereocenter is in principle prochiral, right? Because if you change this carbonyl, now the molecule becomes chiral. So how you can sort of how you can basically discriminate between this one over this one is to have some type of internal chirality to the molecule itself, right? Diastereoselectivity is something that can happen, but an enantioselective reaction, simply taking two components and reacting them together and making them react enantiomerically pure, you can't do. There needs to be some type of component. You can't just create absolute chirality from nothing. But from this standpoint, right, if we can bring in something that could allow that relative diastereoselectivity, if you will, in a way that wouldn't necessarily be, or in a way that would be reversible, that would be very powerful, right? And so this is what we're going to sort of translate to, and we're going to discuss a little bit about next class. And that's enamines. Okay? Because much like enolates, another type of nucleophile that's derived from ketones are enamines. Okay? And this is when you have a ketone. And again, we've already seen this chemistry in the past. You take this molecule, you treat it with, say, for example, a cyclic amine. Okay? That cyclic amine will condense through condensation chemistry, right? And it's going to tautomerize. Or not tautomerize, it's going to get deprotonated and then resonate. And then what we're going to have is, right, enamines. And enamines can behave nucleophilically, right? Because you have the lone pairs on the nitrogen. They're certainly better donors than, say, an oxygen, right? So an enol might not necessarily be wanting to do this, but in many ways, these enamines can behave in that way. Now, I've drawn this molecule on purpose, in part because this is the core component behind a pretty much the only secondary amino acid that we have. Amino acids are obviously chiral, right? We'll discuss them a little bit later in the semester, but this is proline. Okay, proline has stereochemistry at this carbon here. Okay? Now, this chemistry, you can do all that chemistry, a lot of the chemistry that I just showed you that you can do with enolates, and we'll discuss this a little bit more next class, you can do with enamines. And so, if instead of running this reaction with just the base, this will be the intro to next class, if we instead treated this with, say, for example, proline, you can get a single enantiomer, you can treat it to this system. What's going to happen is Now you've got a nucleophile, and not only do you now have this nucleophile, but what you've done is you've installed stereochemistry into that nucleophile, so you only have a single enantiomer at this position. And now, this is not an enantiomeric process, it's effectively a diastereoselective process, because this stereocenter over here can actually induce this molecule, and I don't remember which one it would necessarily react with, but it will allow it to react with one of these carbonyls over the other. Thus, you can get a single enantiomer. And so this is actually the first example of asymmetric catalysis using what they call sort of organocatalysis. And again, when the product's done, you end up to a species like this. It hydrolyzes, and you regenerate the carbonyl. So we'll discuss next class a lot of chemistry involving enamines.
Hi, everyone.